let's talk about conditional expectation. The idea here, like expectation, actually pretty straightforward. If expectation is a population average, conditional expectation is a subpopulation average. That's it. So expectation, you can think of like, if I take a random person, what should I expect their age to be? It's called expectation. What's the population average age? Conditional expectation is if I sample a random person from a subpopulation, so here country X, what should I expect their age to be? Or what's the age of the people in this subpopulation from Uganda, from Venezuela, whatever. So going back to our definition of expectation as a average in the population, what I've done here is I've written out the denominator instead of big N as 1 plus 1 plus 1. How many ones are there in the denominator? Exactly big N, because there's one corresponding to each of these people. So if I just get rid of a bunch of terms, and I'm only keeping what I'm doing here is I'm checking for each person. I look at their value of a different random variable, y. Okay, so maybe X is age, maybe Y is what country this person was born in. So I'm just checking for each person, were they born in this particular country? If they are, I keep them. So that's what I've highlighted here in the pink. If they're not, I get rid of them. So I cross them out. And then the terms that I keep, I'm bringing this down here. And so again, I'm doing this in both the denominator and numerator. So I'm bringing this down here, and what I'm left with is a total number of ones equal to n sub y. So this is the number of people that were born in this country. And on the top, I have the sum of all their ages. So what is this? This is exactly the population average age just among the people who live in this particular country. And the way we write that is like this. So this is an analogy to our notation for conditional probability. Now we're talking about conditional expectation. And what is this? This is this thing is a number. Okay, it's a number for each value of y. So it depends on what country we're talking about, right? The average age in Venezuela is different than the average age in Mozambique, is different than the average age in Hungary. And so if I put in a different little y here, the thing that I get out is a different number, but it's a number. And it's a fixed unknown number. We generally don't know what it is, but you imagine that it's some fixed quantity. So let's have an example here and show you how you can compute this thing with sampling. So I'm taking a really big number, 1 million samples from a population that has some jointly distributed variables x and y. X here is being taken to be a random number between 1 and 10, integer between 1 and 10. And then y is a normal variable where the mean is the log of x. And if I take my samples, which we can think of as approximation to the population, what I'm asking about here is what is the mean of y. Again, slightly different notation than I was doing it before. You can do the $sign thing here and not need to summarize, and that's nicer, I think. But if you calculate this out, you're going to see that this is the overall population average, and you're going to get the number 1.51, I think. And if you ask, however, to first group that data frame by values of x, so you're going to have all the people who have x equals 1, all the people who have x equals 2, and so on and so forth. And then within those groups, compute the mean of y. What you're going to get is this. So here you have a data frame where you have for every value of x, you have the subpopulation mean of y. So for the people who have x equals 2, the mean of y is 0.69, and for 7 is 1.95, and so on and so forth. So this is a conditional expectation. Given x, the conditional expectation is a particular number. But if you talk about the conditional expectation without a specific value for y here, or in this case for x, because we're switching the roles of x and y, if you don't have a specific value here, and you just say y given x with no equals little x, then it's this whole table, which you can think of as a function where you give me x and I give you back the conditional expectation of y given x equals x. So this y given x is a function. We'll see more of that later. All right, let's do this problem. Make a little simulation on y. And I think this is actually the same one that we had before when we were looking at the densities in the previous video. And the question here is just, can you approximate the expected value of z given that y equals 0? And then I have some other questions here approximating some other conditional expectations. And let's give that a shot. Oh, okay, so it's not exactly the same. This was uniform, and now I have Bernoulli. You know what? So I need to define that. Okay, what is this? So I could just call R binom with this parameter set to 1, but that's kind of annoying because I'm not going to use binomial. So this is just like a special case of this function where I've hard coded this argument to be set to 1. So now I can use it like this, in case I haven't mentioned that before. And then of course I forgot to delete that. Oh, gotta make this default 0.5. Great. Okay, so now we have this population. And our question now is, can we closely approximate the expected value of z given y equals 0? So this is just the average value of z in the subpopulation where y is 0. So all I need to do is take the population and just get the people where y equals 0, right? So this is step 1. And now I just need to get the average value of z in this subpopulation. Done. Okay, minus 1/2. And you should know, you should recognize this as a correct, because if y is fixed to be 0, this line here doesn't matter, right? So just cross this out. Let's say in the subpopulation where y is 0, there's just a 0 here. So then z is x. For that subpopulation, z is just x. And what is x is a normal with mean minus 0.5. So the mean of z when y is 0 should just be minus 0.5. And that's basically what we get here. Okay, cool. So now, question 2, can you approximate the expected value of z given x equals 0? So here we have y equals 0, here's x equals 0. So let's try to do that. Can't we just adapt this approach? So now I just need a condition on x being equal to 0. And it breaks. Why? Why does it break? Let's get rid of this. Just run this. I get nothing back when I try to filter on x equals 0, because x is a continuous random variable. So I actually have nobody in my population whose value of x is exactly 0, right? So that does not work. So what, maybe a workaround here would be to, instead of filter to x equals 0, I can try to get x close to 0. So maybe between minus 0.1 and positive 0.1 or something like that. Okay, so that works, but it's kind of awkward because you'll see that if I make these numbers, so this is maybe a bad approximation because I'm not conditioning on x equals 0. I'm actually conditioning on x is between minus 0.1 and 1. And if this conditional mean varies wildly as x changes even a little bit, then maybe this approximation could be very bad. And some might think, okay, I'll just make it tighter and tighter, right? Maybe I'll make it quite narrow, 0.01 or something like that. And in this case, it works great. But you'll notice that as I make these bounds tighter, the number of rows that I end up with here gets smaller and smaller, and you end up with not really a good approximation at all. So with continuous random variables, this kind of sampling way of approximating can be a little tricky to get good approximations. However, in this case, you actually don't need to do this at all. You can just look at this and tell me exactly what the expected value of z is given x equals 0. Because it's the same as we did for the other case where y is 0. So here, if I'm telling you that x is 0, then z is just equal to y, right? And y is Bernoulli 1/2. It's a coin flip. So the expectation of this random variable is 1/2. So the expectation of z given x equals 0 should just be 1/2. Okay, so here we are talking about conditional expectation as a function, where you give me the value that you want to condition to, like, for example, what country was this person born in, and I tell you what their average age is of people in that country. So that was a case where the variable being conditioned on was discrete, like what country. But you could also condition on a continuous variable, like we saw in this example here. And so in this case, for any value of x that I'm putting in here, I'm getting at a different conditional average for z. So let me show you here a kind of joint density between two continuous random variables, x and y. And what I am showing you here is what happens if this is the conditioned random variable x, given that I fixed y to be some value y. So this little value here is little y. So when I fix y equals to little y, this is the distribution of x that I get. Okay? And so I can ask, what is the mean of that distribution? And that's what I'm showing here. So I've just taken that over here, and then I'm asking, what's the mean of that? And in this case, it's 0. Okay, now I can change the value of y a little bit. I can put y equals here, little y equals here. And I can ask the same question. What's the mean of x when I've moved y a little bit? And so for every time I'm fixing y, I'm getting a number out. And that number is this mean. So for every value of y, I have a number, which is the conditional expectation of x given y. And I can plot those things. As I move y, what's the conditional expectation? And that's what I'm going to show you here. Well, we already talked about this. So here's an example. Y and x have some continuous joint density. And at each value of y, I take the expected value of x. So here, it's this value. But if I change y a little bit, let's say I move y down here, right? Then my distribution of x is shifted a little more in this direction. And so my conditional expectation is over here. It's a little bit bigger than it was over there. And so I'm kind of just like tracking the conditional expectation. In this case, by the way, it's like this ridge because my densities are like unimodal. But remember that the expectation is not always the highest point in the density. If it's bimodal or something, it depends how on the shape of the density, but it's usually not actually the kind of peak. But in this example, it is. So another way of looking at this is like this, where I'm kind of looking top down onto this density. So the darker regions indicate areas where there's higher density. There's more people in our population are kind of have values of x and y in those regions. And what I'm showing you is if I'm slicing along at a particular value of y, and I look at x and I say, what is the mean value of x? Right, that's this line here. And I pick that and I put a pink dot there, and then I shift y over and I keep doing that. I get this curve, and this curve is exactly the conditional expectation of x given y as a function of y. So you tell me y, I tell you what the conditional expectation of x of given y is at that value of y. So I'm using this little mu notation. Here, this is just what I've chosen to call the function. I could have called it g, I could have called it q, whatever. But mu is often a popular choice, and this is simply defined as this conditional expectation. Mu is a popular choice because the mu is an m for mean, so a lot of people use that, but it doesn't matter. Call it what you like. The point of this is just to show you that the conditional expectation is a function, as if you don't specify what value you want to be conditioning at. If you do, you can just take the value of this function at that value. You can also get the conditional expectation from the conditional density. And this, you can, again, stop the video here and go back to our argument before for how we computed expectation from the population average and then move that into computing it based on a density. You can do the same thing. The only difference is that now you're in a subpopulation, and so the density you get out is not the marginal density of x, but it's the density of x in the subpopulation where y equals y, which is exactly this conditional density. So there's a lot of stuff flying around, so I wanted to stop for a second and think about what is the notation and how does it relate? What kind of objects are we working with? So I have these symbols here. Omega, I'm just saying, think of this as the population, like the set of all people, little omega, little 1, little 2, so on. And this is a random variable, an expectation, a conditional expectation, some densities, and we just want to figure out which of these is which, okay? So some of these, multiple of these can map to the same kind of object. So just think about this for a second. Okay, let's start with population. A population is, we haven't really talked about this too much, but this is a set of people. What is x? X is a random variable. So it's a measurement. It's a measurement that we take on people. So it's actually a function that takes a person and returns a number. Okay. The expectation, this is a population average of this measurement, which is just a number. This thing is, for each value of y, it's a number. So you give me y, I give you back a number. That's a function that takes the number y and returns a number. This is our density of x, which is a function of a number x. You tell me what x is, and I tell you what the probability of seeing that is for a discrete value, or otherwise just the value of the density, the relative likelihood for continuous x. The joint density and the conditional density are both functions of numbers x and y, where you give me what x is and y is, and then I tell you either what the conditional density is of x at the point y, or I give you the joint density. Hopefully that's just helpful clarifying these concepts. Okay, another question here. Make a data generating process. And honestly, I've been giving you a lot of them, but let's just do it from scratch if you can. Where x is a standard uniform distribution. That's pretty straightforward. Now I'm going to tell you why. Let it be any distribution you want, but you have to construct this joint distribution such that the conditional mean of y given x equals little x is the value x. So struggle with that a bit. If it's obvious, great. If not, that's no problem. We'll work it out. Okay. So how do we set y here? I want the conditional mean of y to be x. So when here's one way to do it. Done. Okay. So the way I've set this up. Well, what is y, given that I know x equals x? So if x equals little x, right? The way I've done this, y equals big X. So if x equals little x, then y is just going to also be exactly little x. And so here, this has to be the mean. Everyone in this subpopulation is going to have exactly valued little x, and so the mean of those will be little x. But there's other ways you could do this as well. So it does not have to be so simple. I could do a normal random variable, and I just have mean of x. Something like this. So now at each value of x, y is a normal random variable, but its mean is exactly whatever value that that x took. So this also works for this problem. And there's many other things you could do as well, but these are two simple choices. All right, couple of quick properties here. I think conditional expectation is also linear. Conditioning, so here I have three values, x, y, and z. If I condition on a particular value of z, all this still holds. The proof of this is exactly identical to what we talked about for marginal expectation. This notation here that I've written, remember that when I don't have a value like equals little z, I mean that this holds no matter what value of little z you choose, right? So this is a function of z. We're saying that this function of z is equal to the sum of this function of z and that function of z. That's one way to think about it. Another way to think about it is that the number you get on this side when you condition to a particular value little z is the same as this number plus this number over here.